Okay. Okay, so today we'll continue on from last week with the second half of the implicit models lecture. So last time we were we looked at the motivation, the definition of the original GAN, and then we had some evaluation metrics, the parse and inception and the Fichet. And then we had some theory, the optimal discriminator, how the GAN, the original GAN optimizes the Jenkins-Shannon divergence, and some ways to avoid mode collapse and avoiding saturation. And then we looked at the first iteration of GAN improvements with DC GAN. So we'll look at today. It's just these three points, or actually just this point, this line, and then until the end of the first one, first style GAN. So the rest will be in this the next 2 hours of lecture. So we'll just go over some different versions of GANs that have been proposed. Okay. So the first is this paper, some techniques from this paper called Improved Techniques for Training GANs from 2016. Okay, this is called feature matching. Yep, it's feature matching. So here, this is the equation I copied over. So F are the activations, or also, so then it's also called a feature, but it's the activations in the intermediate layers. So instead of the final layer that's saying classifying it as a fake or real, we actually look at the activations one step below. So it's not the final decision. So by making sure that the low-level features also match up, then the training is improved. So X is our original, Z is the latent, and then the generator, and then we make sure we pass it through. So F is our discriminator here in this case. So we look at the layers before the final fake or not fake, and then we take the norm of them. It could be, I think it's L2 norm, but it can be a norm, and then we say, okay, that can be the part of the loss function. Okay. So this is the mini batch discrimination. So okay, so this one I had some some notes on. So this is to avoid something called mode collapse, and so this happens when no matter what Z is the input, the output is the same or very similar. So this is one of the examples I found here. This is the link here. So you generate all these, and then they all look almost exactly the same. There's just minor variations of it. I think they were trying to generate anime faces. They all look like the same face with slight variation. So what happens is discriminator is then fooled by one good example. So this is a fake one. And then the generator just keeps making the same. Because the gradients all point in the same direction for training the generator by the discriminator. So, but then what happens is discriminator learns that this is a fake, because if you just get it from this mode, then it's fake. They'll just learn that it's fake. Then what generator does is it switches to another output that is all the same, but but in a different mode, and then it fools the discriminator again, and then the discriminator is fooled for a little bit, then it learns again, and then you're constantly switching modes. But the problem is that there isn't a variety of these images. There just produces the same one. So the way to so the problem is the discriminator processes each example independently, and so all the gradients all start to point in the same direction. So the solution is to do multiple data in combination. So use data from other examples to use the site information. So their goal here in this paper is to figure out how to model the closeness of images to each other. So, it's pretty involved. So fxi, the same notation before f, is the features of some layer, with the xi is the image. So what we have is some matrix T, and we multiply the T, and then we get M. So you have these features, and then you get all these different M's for each feature by multiplying it through this matrix T. And then you compute the L1 norm between the different samples. So this is for sample xi, and then you calculate the L1 norms between the B is the same here, but then the I and J are the different samples. So it's the same. So M1, M2 is the second or the first feature, but it's different samples. And then you combine them together into O vector. And then you create another O vector of all the different samples with all the distance between all of them. So this is very involved, but all it's doing is saying, here's image one, give me some way to say how far I am from every other image. And so this is just added to the neural network in the discriminator, I believe. Yeah, so the discriminator gets discriminator knows if the generated samples are too close to each other. So that's another technique. But this is rather involved. But the idea is simple. Is you have features, you pass it through some set of transformations, like the T here and then the M here, and then you get some measure of how close they are, and then you have a measure of how close they are to each other, and then you add this to the add this to the neural network. And I believe this is the discriminator, or maybe it's to both. I don't know. Okay, but we can move on. Okay, so the third technique they're using is called historical averaging. So this part is added to the loss, or loss or cost. I call it cost, but it should be loss. It's just a regularization term so that the theta does not oscillate. So the new theta must be, if it moves too far away from what it's been in the past, then it will have a huge cost. So so it's just to make sure that the theta moves in a slow manner instead of just jumping around a lot. Right, historical averaging. Okay, and so the fourth technique is called the one-sided label smoothing. So this is the default discriminator cost, right? The you want the first part is the real part. The data is the real part. You want it to be 1, and then for samples you want it to be 0. But it's good to add a little bit of noise. So instead of being 1, you set it to 0.9. And then but you think that this would be 0.1 because there's 0.9 here and then 0.1, but apparently this would be a problem. So if you remember this was our optimal optimal solution, optimal discriminator. So if we start adding the model also there with beta, and if this is a generated data, so P model is the that creates X from Z. So if it's here in the numerator, then this can cause a problem. Suppose we're not using data, we're using model, then the discriminator can also learn this part. So this will have a huge value and can cause problems. So from what they say, it reinforces the current generator behavior. So yeah, this probably needs to be put back into that equation to see what it actually is going on. But they say we shouldn't have this term at all. It should just be 0. So they set this to be instead of 0.1, it's 0, and this part 1 minus alpha is 0.9 to add some noise. Okay, this one is a virtual batch normalization. So so in this case, they use a reference batch to compute the normalization statistics, and then use those statistics to normalize a batch. And so, but the problem is you overfit to the reference batch. So then, or you need a very large reference batch. So both are problematic. So it's so the new samples to the reference. So you add the current samples into the reference batch to create a new batch for normalization. Otherwise, it generates very similar looking, similar colors images. Okay, so those were the 5 improvements. So I can go back. So the feature matching, where we matched lower level features other than the final one. Mini batch discrimination, where we looked at the distance between the images, the features of the images. Historical averaging, regularization by using the history. Virtual batch normalization. Oh, this got switched over. One-sided is where we set the probability to 0.9 instead of 1, but not for the generated data. And then we have the virtual batch normalization, where we have a reference batch to normalize, plus we add the current batch so to normalize. So these were the tricks that they used, and it worked. So and then also started this semi-supervised learning. So in addition to just saying if it's fake or real, and if you have data that already also gives you the category, then you can also add that in there. So so you can model what is the class of the image. Okay, so so the idea here is that we have k labels of the images. So we'll have 1 to k, but we'll add another label to it, to k plus 1. The k plus 1 will be the fake label. So the system has to detect, or sorry, the discriminator has to say which class is this? Is this cat? Is this a dog? Is this an airplane? Or you can say, well, no, it's a fake. So there are k plus 1. You add 1 extra from what the data set has. So the loss function here is that you want for the you want to be able to detect the class given X, right? So and so depending on the this will produce the this will give you the probability of so X has actual class Y, and so you're saying log of probability of the model Y over X. So this is like the what is the probability that you correct guessed it right, and over all the data, and then you remove all the ones and you say what is the probability that you guessed that this was a fake, that Y equals K plus 1, it's a fake given the generated data from the model, and that's the loss function, right? And just with some um, this second part shows that this loss function can be cut into two different pieces, the supervised part and the unsupervised part. So then we can see that the supervised part, we start with this one, and then we don't care about the fake label. So we'll say Y is given X and then Y is less than K plus 1. So Y has to be 1 plus K. So that's the supervised part, right? That's the part you would do if you were doing just the supervised learning for classification. And then whatever's left behind, so this is the part where Y is K plus 1, and that it was a generated and then it was detected as fake. So this is the unsupervised part and this is the supervised part. And if we look at it, this looks just like the GAN formulation, and this looks just like the classification. So you can just put these two together into one by saying labels 1 to K and label K plus 1 for fake. So you can do both at the same time. And doing this improves the GANs. Okay, and so this is the inception score, and we already talked about it. So we can just skip it. And just for review, it's just you take the features and you get the distance between the features. So we have p here, but you could think of it as f. It's the features, and the features are through the inception network for classification. Okay, and this was the stuff they generated with the improved ones. I mean, it's still, it was pretty good, I guess, for their time that you can generate these kind of things that look like a dog mesh with something else. Okay, any questions on that? Or I can move on to the next one, the WGANs. Okay, so let's look at the Wasserstein distance. So the main motivation here is that we use the KL divergence for the latent models, right? For the previous lecture. So for VAEs and things like that, we had the KL divergence between the real and the generated, and we had the equation, all of that stuff. And then for the GANs, the original GANs, we had the Jensen-Shannon distance, which is the KL divergence between the average and KL. This is a distance metric, and so we discussed this that last time that this came about. The actual loss function was actually Jensen-Shannon distance, And then in the VAEs, we had the KL divergence. So the idea is, well, can we have another distance? And this is another distance that's used, and it's inspired from the optimal transport, the Earth mover's distance. Okay, and so I have some slides here. So this is from a different lecture, but also in Berkeley. But it's the deep learning course. The problem with KL divergence and Genshin Shannon was that it had no notion of distance. So these two would have the same loss, even though they were very far away, right? So in order to, it has no notion that it's trying to get it closer. So once they start overlapping significantly, then the problem is solved. But when they're far away, it's kind of hard to get them to overlap, because it could be anywhere, and then the cost is always zero, non-overlapping, or the distance is very high. Yep. And so they came up with this Earth mover's distance. So the basic idea is, how far do I have to move stuff from here to create this other distribution? So so let's imagine distribution and distribution 1 and 2 as mounds of Earth. It's in one place, the other one is another mound of Earth. So these are two distributions, right? So the question is, how much Earth do I have to move from distribution 1 into distribution 2 to make it look like distribution 1? So I move some Earth around, and then how will they look similar? And so I probably will have to move some Earth backwards also, and also sideways, right, for different places, and then also height-wise. I mean, here both are Gaussians, but I think if it's a taller Gaussian than a flatter Gaussian, then it would have slightly different distances. So the idea of the optimal transport is, what's the minimal amount of Earth I need to move? So the Earth moving is like, how much Earth do I need to move so that they're the same distribution? So the optimal transport will say, what's the minimal one of the Earth mover distance? So in this case, it was, I guess it would just be the distance between the means, because you can just move them all around. So that we need to have a formal mathematical definition of it, of what this means. And so this is kind of involved in how this is defined, right? So okay, so let's look at this one. So we have W, which is the Wasserstein distance between P data and then the generated. Okay, so first of all, there is this thing here called the gamma of xy, where x and y come from. This is defined as the distribution of over x comma y. Okay, so but what it's saying is, this is a two-dimensional distribution whose marginals along x is p data of x, and whose marginal along y is p of g. So we're taking our p data on one dimension, pg on the other dimension, and creating a two-dimensional structure. But then we know that on one axis it's p of data, the other axis is p of g. So there's a lot of different distributions you can make, right, with this property. But and then, so this is a set of all of these distributions that's possible. So it's hypothetical. It doesn't show you how to make it, but it's just that let's look at all of them all of these functions where the marginal on one side is px. Okay, so all the x and y's are messed up. I don't. But one side is p data, one side is pg, and then we're creating a two-dimensional thing that has marginal p data and pg. And the main idea on what to do is you subtract x and y, and you can see this is the distance, right? And so this would be like, how much earth do I have to move for each of the points? And then you take the expectation of all of them, because then you have a height and a probability. So how much do I have to move things around so that that the difference between them, what is the difference between all of them? And infimum means that it's the smallest distance. So we'll have to find the exact distribution, which the x and y are marginal, and then this difference between all of them are exactly the minimum. So we'll find this perfect one that maps each one to the other one, each distance to the other distance, and we have the minimum amount of effort to move this and turn this distribution into the other distribution. So yeah, this is like this is a very abstract definition, right? So it's kind of hard to kind of look at it first, but you just have to remember this is the distance, x and y, and we just want the best distance among all the possible distances for everything, how much earth we can move. So let me go back to the original slide. And I think the notation is slightly different. So here it's this big gamma. This is gamma, right? Yeah, the big capital gamma, and this is small gamma, and the small gamma is here. So for every gamma in this big gamma, that is the two-dimensional distribution with the marginals PR and PG, and we want the expectation of the distances, and then it gives you the Wasserstein distance, and you can see this. You know, it's what's going on is how much do you have to move to turn one into the other. So it's just so the main idea is we have KL divergence as as our cost, and Jensen-Shannon as the other cost. Now we have, we can have another difference between the data and the generated, and see if we can use this as a loss function. Yeah, and then so we want to see again function that minimizes the Wasserstein distance between the data and the generated distribution. See if this is so. This is the idea behind the Wasserstein distance. Okay, so obviously it's impossible to. I mean, it'd be very hard to find all these two-dimensional distributions with marginal PR and PG. Like going over it seems intractable. I mean, it's intractable to estimate, or it's intractable, and would have a good way to estimate. But fortunately, we have something called a dual of it. So it's called the Kantrovich-Rubinstein duality. It measures the same thing, but it's a slightly different formulation of it. So but this is not like, this is intuitive. We're seeing some distance here. We're seeing Earth being moved around, but here it's the same equivalent mathematically, but we don't see that. So okay, so let's go over this formula. So it's the distance between the distribution PR and PG. So we take for each x, we take f of x from the real, and then the f of x from the generated. And what is f of f? It's some function which is Lipschitz. And Lipschitz means, if you, this is from, I think, calculus or something like that. if you have 2 points x1 and x2, then it means that f of x1 minus f of x2 must be less than or equal to x1 minus x2. K, I think, yeah, I made a mistake here. The k should be in front here. There should be a k here. But yeah, basically means that you take a function f, and it shouldn't um, blow up the values of x in a different direction. So this distance between x1 and x2 and the distance between where f takes x1 and x2, they should be smaller. And I think there's things like continuity, Lipschitz continuity, and other things. So it basically gives it makes things smooth. It gives a speed limit on how things can move. So it makes things move slowly and with I guess the mathematical intuition is that it kind of like smooth and with a speed limit, having a Lipschitz function. And so the idea is that if we take a Lipschitz function and then we take the real and then we take the expected of the generated, we want to find the Lipschitz function that maximizes, sup means maximizes this expression. So it's the answer here. This distance is the same as this distance. We should get the same number, but this is a different formulation. It's a dual of it, and the dual just means it's like you can derive them from each other, but with some by solving things around. So it's the same property, but it's with a different formulation. So before we had to search over all joint distribution, now we have to search over all Lipschitz functions, one Lipschitz functions. So so maybe this is a slightly simpler problem, or this is more tractable to do than searching over all joint distributions, or there's some techniques for this. Okay, so when we do the Earth movers, the optimal transport distance, or the Wasserstein distance, it has multiple names. We are now going to just look at this formulation. That yeah, that doesn't seem related to the distance and all of it, but we just have to trust it's the same one. So we don't go into the proof, but it just have to trust that it's the same thing. That this is still like moving Earth from moving the distribution from one place to the other, and how much it would take to move it. Okay, and so this is the paper and the Kantrovich-Rubinstein duality, and this is the same formulation we looked at. And then we take the supremum over k Lipschitz functions. It gives us the Wasserstein distance. Okay, so this is the definition of the Lipschitz function. It's a little bit generalized. So instead of the double bars, we have the dx and the dy, which are the distance. But it's the same thing, but instead of the bars, it's a more general way of saying the distance between these 2 points and then the distance between x1 and x2. And then you have k for the Lipschitz. So how do we search over all of the FWs, all the Lipschitz one functions? What technique can we use? And so since we're doing deep learning, of course, then this is a neural network model. Anything we don't know how to do, we just put it in a network, right? So this is going to be a part of the network that it will generate the F. Okay, and so this line here, Okay, there's two things going on here. So sorry, this looks very messy, but so let's just look at the first two here. This part. So this is the same, but it's saying if you look at it, the expectation to PR is still there, and then we have FWX instead of FX, and then this is the same, and this becomes FWFX, right? And then the W is this FW is deep learning. It's our model FW with the parameters W. Since this is the supremum, which is the max, it means that whatever our function FW is, it's going to be worse than the optimal, or maybe it's as good, but it's going to be always going to be lower than that. So whatever we come up, it's the distance is going to be less. And so let's look at this side here, these two parts. So what they're saying is the way we defined it before is that all the functions need to be Lipschitz 1. And so in this case, if we put k here, if it's a k Lipschitz function, then we can just put k in front of the Wasserstein distance. So that also has another advantage, is that we don't have to, this can be any function. And then if it's any bounded function, as long as it's bounded, as long as it's less than k, then it is less than the k times the definition of the Wasserstein distance. So we're good here in the sense that, you know, our distance is always going to be less than k times the optimal distance. And then for PG induced by G theta Z, we can backprop through. Yeah, and then it's saying that G theta is our generator, and then PG is the distribution of the generator, and we can use backprop through this expression that has W's in it, because this X has the Z theta, so we can still backprop through it for the generator. So we don't have to be worried that this will cause any problems. The FW can, having parameters in FW is also fine. Okay, so let's look at the Wasserstein GAN pseudocode. So I have the original GAN here. So look at how we did it. So this is the part where we are training the discriminator first. So we sample M noise samples and generate, and then examples, M examples, and then we update this discriminator using log of D plus log of 1 minus DG of Z. So that's the standard. And then you take the gradient and use the gradient of this to update it. After we're done with it, we sample more noise samples, and then we update the generator. So the generator gets the gradients from the discriminator, and it's updated, and then we go over and over again, right? And then we made a small change from the original one, so that the discriminator is still doing the same thing, but the generator is now doing, instead of 1 minus D, it's just negative of log of d of g of z. So this was to prevent the saturation last time. So instead of doing 1 minus dg of z, and that caused a flat area. So if the discriminator got too good and it became confident, then the gradient would be 0, and then it would stop learning. But with this formulation, it still had some gradient, so it could still learn. And so those are the two formulations. So let's go back to how this is different from the Wasserstein GAN. Okay, and critic, it has a slightly different way of writing things. So okay, so the critic is the they're using slightly different terminology. I think it's actor critic, which is the same. The critic is the discriminator, the actor is the generator. So so you can just think of it as the critic is the discriminator here. So we sample, just like in the other one, from the real data. PR is the real data, and ZI is the distribution of latent variables. And then just like the Wasserstein distance, with the supreme version of it, so we have 1 over m of sum of fw of xi, and then fw of g theta of zi. This is just like we in the Wasserstein distance, this one, right? But the sup became max. The expectation is still there, so it could just be 1 over n of the summation. So the expectation became 1 over m of the summation, and then we take the gradient and update it. Here, the w are the weights of f, which is the Lipschitz function. And notice that the Lipschitz function fw is also working as the discriminator here, but it doesn't produce numbers between 0 and 1, but it still produces some real number. And so here is the one that they did here, is to clip the values of the weight between negative c and c. So if the weights are bounded, then this comes into action, that perhaps all the functions are less than k, because all the weights are just linear functions. And so this would be valid. They do say this is not the best way of doing it, but this is a simple way of doing it. And so this is part where we train F, or the critic, or the discriminator, and then outside we sample, and then we update theta, which is the parameters for the generator, right? So this is the Wasserstein GAN pseudocode. So here's the main thing where they enforce the Lipschitz thing, is just by doing the clipping. And the idea is that if you clip it, then probably the function is less than or equal to some k, and so it is less than or equal to some number times the Wasserstein distance, and so it should work. Okay, and I think this was the main surprising thing. So we have the blue one, which is real data, and green one, which is the fake data. So this is the 1D dimension, 1D data, and then the GAN discriminator is basically like goes like this. So if you go on either side, the gradient can become 0, and you'll stop learning. And there's just this very limited range which you can learn. Otherwise, the discriminator can become 0 and it wouldn't learn. But with the Wasserstein WGAN, it has gradient all the way through, and it's actually linear. And so that makes WGANs much easier to train. That it's not going to have problems in training. And the Wasserstein distance actually also, so the lower the Wasserstein estimate, the better the image start looking. But it's not necessarily with the JSD estimate. It can look good, but the numbers are still kind of just moving around. So in the sense that Wasserstein estimate is also produces better images, also has a much better range in which it will converge. And this is WGAN more examples that they generated. And this is from the bedroom set. And it's pretty fuzzy, so. Okay, and I think this is batch norm not working, or DC, it's just comparison between DC GANs. I'm not sure, okay. And this is the difference between WGAN versus standard GANs. Okay, so this is the summary. So this was the standard GAN equation. Log of the we want to maximize log of the discriminator, and then minimize the log of the discriminator of the fake ones. Wasserstein distance, we want to find the max D, which is going to be the FW in our case that we're talking about now. Now it's D for the discriminator, and that that minimizes this distance, D of x minus. So this is the f of x part minus f of y, f of or g of z part. Right. So this is the difference, and this seems to work much better than the original formulation. Okay, so this is the summary. So we have a new measure of optimizing the generator. Some of the instabilities are addressed. So robust architectural choices. So we can use the different CNN architectures and resonant architectures, and a little bit better progress on mode collapse and derivatives. And then the idea was to use the Lipschitz to stabilize GAN. Okay, and the negative is weight clipping is obviously a bad idea. So we have to set a hyperparameter for the weight clip here. So sorry, going back quite a bit. Here we have to set the hyperparameter minus C and C or C clipping parameter. But if it's too big, it causes problems. If it's too small, it causes more problem on other problems. And so this paragraph basically says that clipping is probably the weakest part of WGAN. Okay. So can if there's any questions, then or I can move on to the next one. Okay, I'll move to the next one. So this is more improvements to the WGAN. Okay, so this is a big theorem here, but we can try and break it down, what it's saying. But most of the stuff we already looked at, right? So we have PR and PG. So the data PR is the P real, and then the PG is the generated model. So you have two distributions, compact metric space. It just means that it's in a nice smooth place, not spiky place. And it's just for mathematical reasons. For algorithmic, I don't think it matters, this compact metric space. Then there's a one Lipschitz function f star, which is the optimal solution of max f. So this is the I forgot the name of it, but the dual of the Wasserstein distance part, right? So we have Lipschitz that's less than 1, and then the expectation of the prob of f of y and expectation of f of x. Some of the letters are slightly changed, but you see it's the same thing. So it's saying the same thing as before. Then that there is an f star, a Lipschitz one function that we can find the Wasserstein distance for. Let pi be the optimal coupling between PR and PG, defined as the minimizer of the original formulation of the Wasserstein distance. So we have x minus y expectation over the two-dimensional with the marginals that are PR and PG, and then we take the minimum of it. Yeah, and is the central joint distribution since marginals are PR and PG respectively, right? So this is all the stuff we already know. So this is just like setting up what we already know. We have PR and PG, we have the Lipschitz style of Wasserstein distance, and then we have the other method of Wasserstein distance, these two ones. Okay, so that's all it's saying. So here's, I think this line is the main one. So if f star is differentiable, so if it's smooth enough, it has certain properties. And so I think this is a complicated way of saying x is not equal to y. I think it's saying the probability of x equals y equals 0 means that basically x is not equal to y. I'm sure there's like some reason for mathematical reason for stating it like this, but we can just think of f star is differentiable, x is not equal to y, and then xt is equal to tx plus 1 minus ty, which is the linear interpolation between x and y, right? Yeah, if x and y were equal, then xt would always be x and y. So that's probably why it's there. For t equals 0 and 1, so we have x in one place, and then we have y in the other place, and it's a straight line between x and y. And the theorem says if all of these happen, then this is the same notation, but we can just say the gradient of f, the Lipschitz function f, is y minus xt over the norm of y minus xt. So this is the this is the main theorem. So from that we have a corollary that's actually useful. Then we have this. The gradient is just equal to the difference between them. I guess we can just take the derivative with respect to t here, and that should be about the oh, I don't know. Yeah, but anyway, this theorem says that. But but the simple corollary is that f star has a gradient norm of 1. So if you take the norm of this one, the top and the bottom are the same. So the norm is 1, right? So if you take the norm of this one, so it's saying f star has gradient norm almost everywhere under PR and PG. So if we have this optimal one, then its gradient, the norm of the gradient is always 1. So this basically the theorem says we have this one Lipschitz function, and if we have such a thing, then we take the norm of the gradient, it must be 1. Right? It's like a super complicated way of saying it, but that's that's what it's saying. That's the gist of it. So it says almost everywhere. I think all of this is just probability related. So if saying it's almost everywhere means that the probability of it is 1 and pi of x, this is just, I think, probability talk to for more formal mathematics. But all it's saying is f star has gradient norm 1 and under PR and PG. Okay. So how can we use this theorem, right? So so the way they use it is there's our Wasserstein critic objective here again. So f of x minus f of g of z. So here is the real data, expectation of the real data, and then the fake data, all with the d. D is the Lipschitz function instead of f, so the notation has changed. But we add this gradient penalty. So we take the derivative of the Lipschitz function, take the norm of it, and subtract 1. And so if this is actually the optimal one, this will minimize to 0, right? Because the gradient is always 1 everywhere. If not, it will the loss function will try to squeeze this d towards the optimal one by having the gradient 1. Although I guess you have to remember that it says f star has gradient norm 1, but if it has gradient norm 1, it doesn't say it's f star, but they're using the converse of the theorem. Because this one says if f star exists, then it has norm 1, but if it has norm 1, doesn't mean it's the optimal one. But apparently this works. So yeah, so they're using the inverse, the converse of it. It's the converse of the inverse, I think. But that's not from that is not implied from that theorem, and it hasn't been proved. But it's just I believe that's what's being used here. The opposite of what that said. I mean the inverse or the converse of that. And so just have to, there's like one subtlety here. So there's x, which is the real data, x hat, which is the generated data, and then x tilde, which is the generated, x hat, which is the combination of these. And the epsilon is a random number. Okay, and so this is the algorithm. So we can see it's the same, but the difference here is we have x is real data, latent variable is here, and then we have to create. So we have x, that's the real data, x tilde, which is the generated, and then the x hat, which is the combination of them, and then this one goes into the regularizer. And then apart from that, everything is the same. So the loss function is slightly changed to say the derivative of the discriminator we must try to make it as close to 1 as possible, the norm of the discriminator. So we went from clipping the gradients to some just to some number, to now saying, well, if it's the optimal, then and we set the norm to be 1, we're pretty sure that it's going to be close to the. It's going to be maybe we'll land on the optimal one in one of the training sessions. So so that's enhancement of this. And there's still some more discussions about batch normalization. And so basically from this point, I think they're not doing batch. This one is not doing batch normalization. Okay, and so this one, the robustness part. So this is just tables cut from the paper, but can see they're showing the architecture they used. So for nonlinearity, for the generator, there's ReLU, leaky ReLU, all these different things. The depth, batch norms for the generator and the discriminator. So this is the one they used, and so this is the score that they're able to achieve. So this part says this is the one that only the GAN is able to do. This is where only the WGAN GP is able to do. This is where both of them were successful, and this is where both failed. So if the score is low enough, then both are successful. Sometimes WGAN has more successes. Then we ratchet up the score, the minimum score. Then WGAN can do 88 more than GAN, even though both succeeded in 110. And then it failed on one. So if we ratchet it up again, then we know, then we see how it's 3 times more successful than the GAN, right? It did 42, this one is 147. And if we go up to 7, then GAN only succeeds in a small fraction of it, like, but both still fail, but WGAN can still do a better job. For 9, none of them work. So it is more robust than just a GAN. And that was the point. And so here's some of the examples, and then they do say it produces better. So there's the DC GAN that we talked about before. I don't know what LS GAN is. I don't think we went over it. So WGAN with a clipping, and then this is WGAN GP. So obviously the samples look a little bit more clear and with different architectures. But these are still 2017, so this early days in GAN. And then so it was able to produce more high quality images in the bedroom. And they would, I think this is for classification or inception score, sorry. This is inception scores. It had the best inception scores using CFAR 10 out of all of them. And then there's the supervised and the unsupervised modes. The supervised mode is the one where we have, we also send the labels, right? The 1 to K labels of the image in the CFAR 10. And then the K+1 is the fake one. So the SGGAN actually, SGAN is able to do better, but for unsupervised, it was the state of the art. Okay, so what did WGAN improvement GP give us? Robustness to architectural choices. It's a very so it's a popular GAN. So it's slow wall clock time due to gradient penalty, and then because there's more stuff that needs to be done. and the learning rates have to be low. So it's a little bit. The main idea is that it's a little bit slow. Okay. Any questions before we go to the next one?
Yeah, so a question, how do we implement this gradient penalty? So we compute gradient once with this mixed data, we x hat, right?
Yeah.
And then we, okay, so we need to kind of compile this x hat batch, then feed it to our discriminator and compute the gradient of that, and yeah, then we add this to our loss function, and then we compute gradient once again with this added.
Mm-hmm.
Yeah, and that will be the total gradient,
Yep.
which we will use for the optimization. So we do like extra forward pass here, right?
Yep. I think that W is updated outside of the loop. I don't know why, but we have different samples. Okay, sorry. Yeah. Batch size. M is the batch size. So this loss is accumulated for the M different batches, or M different items in the batch, and then the weight is updated.
Yeah, so I think it in like in actual implementation, it would be in a batch form. Just they just written it this way, probably to make it look nicer in a paper. I don't know. Yeah, or is there any kind of restrictions that you got to do it somehow?
I don't see it. I think it can be batched, but
Yeah.
I don't see it. Yeah.
Okay. So basically, the extra cost for this would be just another computation done by the discriminator on this mixed batch, right? So
Yep.
to obtain our gradient penalty. And okay, so and for that we would have to do both forward and backward pass, right? So that's kind of twice as much compute for discriminator.
Yep.
Okay. Yeah, thank you.
Okay, great. Do we have anything else to discuss, or? Okay, I'll move forward. Okay, progressive GANs. And so this one is, the idea here is that you first have again with 4x4. So you start with a very small pixel set, and then you train until it reaches, you're happy with the result. Then you use the same weights here and add more layers, and then you train again. And then you keep doing it until you reach a whatever high resolution you want. Instead of starting from this resolution and then saying, well, let's just try to train it right with this whole stack. Let's just start with a small one and then increase it. And so they were able to generate some very good looking GANs. I'm sorry, good looking images from GAN output. And so these are some of the examples here of the things they generated. It's also different types of bicycles, different types of TV monitors, yeah, and yep, and more higher quality bedroom sets. And then this famous, I guess it's famous face generation. Because now they're able to do 1024 by 1024. And yeah, more faces. Okay, and oh, he's saying just look at their code, not the paper. Okay, so that's the progressive GAN. I think they're using the same architecture as WGAN or WGAN GP in terms of loss function and things like that. Okay. Any questions or okay? If can go to the spectral normalization. So I think this hopefully becomes this is the sort of the last mathematical part. This will take us to the state of the art of the loss, at least in terms of the loss function, I think, or seems to be from what I've read so far. Okay. Okay, so we have to decode this. Did I make notes? No, I didn't make any notes on this one. So let's just decode what is going on here. So F is our old notation of activations, and X is our input. Theta is the parameters, and all it's saying is this is just the deep neural network in one equation, right? So you take X, you multiply it with W, then you have the activation function. I guess they omitted all the biases, but that's essentially happens, right? All the layers you get through, and then you have the final one. So this is just the deep learning in a single line, and so this is the GAN where we have the discriminator. I don't know what this A is, but anyway, so this is the original version of it, where we minimize G and maximize D discriminators, so that the discriminator can figure out as well as possible, and the generator can fool it as much as possible. This is the original GAN formulation, and this is the Wasserstein distance formulation, where we find the F, which is the same as the D, and it's below K. So this is what we already know, except for this one. I think this just means that A is the discriminator function and F, or it's some constant times the function F, the discriminator here, the Lipschitz function. Okay, this is just the Wasserstein with the this is just the formulation of the Wasserstein GAN. Okay, so the idea here now is to connect Lipschitz to the spectral norm. Okay, so let's just first look at what a spectral norm is. A spectral norm is a norm of a matrix. So A has to be a matrix, so the capital A. And so you basically the idea is you take the norm of A times H, all the vectors H, which are not non-zero H, and then take the norm of H, and then find the max such value. So this is the max of same formulation. So max of A of H. So this basically measures sigma of A, the spectral norm of matrix A, measures how far it can project a project of vectors. So if a vector is of length 1 and if h is of length 5, then we know, and that's the maximum, then we know that the spectral norm is 5. So it has the possibility of taking a vector of length 1 and turning it into a vector of length 5 at most. And so that's the norm of this matrix. And it turns out that this norm is equal to the singular value, or the square root of the eigenvalue, or if you know that, the linear algebra part of it. But that's not necessary. It's just that we just have to find the spectral norm. Okay, and so this function that takes inputs from one layer to the other one, then we can define the Lipschitz norm of this as the spectral norm of the gradient of the spectral norm of the gradient over all of H. I don't know what this H is, but from what I can understand is the spectral norm of the gradient of going from one layer to the other. So okay, so so let's look at this part. What is going on here? So this function that g that takes from one layer to the other, the Lipschitz norm of it is the spectral norm of the gradient, right? And the gradient over all of the h's that are possible, so all of the input values that you can send to it. Was it h here also? Okay, it was h here. So this is confusing, the h in and h out. But this is the input, this is the output. So it's saying it's basically saying whatever input it is, what is the biggest spectral norm possible. And so the gradient of the, since this is a linear function, the gradient is just the weights, right? So, and then this is equal to the spectral norm of the matrix W, because this is a linear function. So all of this basically means that in each layer, the Lipschitz norm is the weight, or the spectral norm of the weight matrix. Okay, and then another property of the Lipschitz inequality or Lipschitz functions is that if you have G1 then composed with G2, this its value must be less than or equal to the multiplication of these two separated out. So if you have one layer going to the other, then the Lipschitz of the first layer and the second layer that this is bounded by the individual Lipschitz metric of these. So in order to, how do we use this? What is the point of all of this? The point is that we want to get the Lipschitz norm of our function f, and this is less than or equal to. So we have two things going on here. So we have f, and so we have this equation that's being used. So it's the Lipschitz norm of each of these layers, and we're using this equation here, the inequality here. So in the neural network, it goes from G1 to G2 to G3 in all these layers. So we can just divide them out, and that's what it's doing. So we have the last layer, and then the activation, and then the one before, and then all the way back to the first layer. And the activation functions, Lipschitz norm of ReLU is 1, so we can remove all of those. Then after that, we have this product, which is the which is mapping from one layer to the other. And we've already seen in the first line that this is just the spectral norm of the matrix. Right, so the F Lipschitz is less than or equal to the spectral norm of all of the weights here. So the spectral norm of the entire matrix W is okay. This, so we can define. Sorry, we can define for each layer. So we can define WSN as W divided by the spectral norm of W. So if we do this, then we know that each W has spectral norm of 1. So the spectral norm is bounded. And then we know that the Lipschitz norm is, again, if we bound all of these to 1, then all of this multiplied together is 1. And so this is less than or equal to 1. And like previously, we wanted to be less than or equal to 1. So instead of putting it in the cost function, now we have it, we can normalize the weights doing the spectral normalization. And then it has the same thing as restricting the Lipschitz norm to 1. And okay, so this is the same. And so I think, okay, so basically saying that this works pretty well. They've generated all the dogs and pizza for it. So this is yeah, this is saying like, but how do we normalize convolution matrices? Okay, so here we have this is just a standard normalization. So your data here is X, and you get the mean and the variance of it, and then you remove the mean and divide by the variance plus some error. So then all of it is between 0 and 1, and you get a scale and offset, and you multiply it so by scale and offset, right? So X came with a certain mu and sigma, and then now it comes out with a different mu and sigma. So it's just a different normalization, right? Okay, so this is just a standard batch norm. So they have this thing called the conditional batch norm. So here the input was just X. We didn't have labels for it, so they added labels for it. And the similar thing happens, right? So so this is in TensorFlow. So if it looks weird, it's because it's TensorFlow code. So then you still calculate the mean and the variance, and then you turn it into a mean 0, variance 1. But then when you calculate the scale and the offset, you have another neural network that will generate it for you. So in this case, it didn't, the scale and the offset were not generated, but here the Y value generates, the label generates the scale and the offset, and then you have the conditional batch normalization. So that depending on the label, it has a slightly different normalization. Okay. And this one is for convolution layers. Conditional batch normalization. Okay, what is, did I, something with spec norm? Okay, so here the use SN spec norm is true. So the dense has a field to use spectral norm or not. Okay. Okay, I think I missed something here. Did I? Okay, maybe. Okay, so so then the problem still is how do we how do we calculate the spectral norm? You know, I know we can calculate the singular values. They have the SVD, singular value decomposition, but you know, if we have huge matrices, I don't think it makes sense to do them. So how do we do it? It turns out that the way they do it is something called the power iteration method. So if you have a matrix A and you multiply by X and you keep multiplying it, the output by A and A and A over and over again, it converges to its eigenvector. So and that's called a power method. So here we want to get the spectral norm of W underscore. Okay, and then reshape. Okay, so here we have V and U, and the W underscore becomes W, and you have the U here. So you multiply W by U, and then you put it into V, and then you take V and something is transposed. Okay, take W and then you multiply it by V. So since W is not a square matrix, right? So you can't do the power method. You can't just multiply A of X by A of A again and again, because it's not a it's not square. So the way to get the singular values is to have two different things, V and U, of different sizes of one size. So you can go back and forth with the other. You can transpose it, multiply it again by the regular one, and then transpose it. So if you have an m by n matrix, you multiply by n, you get an m vector, and then you take W, transpose it, then you have n by m, and then you multiply by the m bit, and then you have an n vector. And so you can do it, you have two vectors, but you can do it over and over again, and then you'll get the singular values. Right, so it's like the power method for non-square matrices to get the singular values. Okay, and then you don't want the gradient, so you have the stop gradient is detach, I think the same as detach. Yeah, and this norm value is they're multiplying the U and B together, U and W together, and then by V, and then getting the norm value. And then it returns the normalized value. But the main trick here is that, well, this all makes sense, right? This is just brute force method of finding the singular values. Just multiply it, you know. The trick here is that number of iterations is just one. So you just multiply your matrix by U and V once, and then get the normalization. So just setting it to 1 works. So this one just runs through once only. So you don't even need this for loop. So it just runs through once, and apparently it works well enough that it's good enough to give the
Isn't
good.
there something strange with this code? Like we use W shape before we have W. That's kind of.
Oh, probably. I don't know. I don't know much about TensorFlow, but yeah, this probably should be
like it might be using some, I don't know. Yeah, but this looks wrong to me. But where is this code from?
it's in the slide. Yeah, it's in the slide. So I don't know where they.
Okay, so they don't mention it. It's probably some kind of pseudocode released with the paper. And
this is TensorFlow code, right? TF. So
yeah, I know, but
okay.
you know, with papers, people often do say like we release a pseudocode in TensorFlow. You know, it means that the code here we write a code in TensorFlow, but this code doesn't actually work. So
Okay.
it's not what we use to produce the results presented in the paper. And maybe that's this kind of, it might have some typos and stuff. I don't know.
Okay.
But this looks a bit weird to me.
Yeah, it makes sense. But I think the main idea is just to show that you do the power iteration, but you only do it once. So it's not even a power iteration. But yeah, all of this like reshaping and all of that is yeah, it's pretty weird. Okay, but and this one is the yeah, and it just shows the dense function. So if you use spectral norm, then it says W equals spec norm, and then you send in the number of iterations. And so W here becomes different. So it's just doing the XW plus B, but the W has been modified. It's just in TensorFlow. TensorFlow language. Okay, con2D. And this is the same for the weights of the con2. I think in the lecture, the lecturer says that when you do the spectral norm of the con2D, it is more complicated because you don't have the weight matrix. You have kernels, strides, you have all sorts of other things. So I think the trick was to just make the kernels into so W is equal to the kernels, and that should be enough. So I'm not sure what this kernels is, but the idea is that you can also do the spectral norm for con2D without having to make it complicated, even though it's not a matrix multiplication. Just doing the basic multiplication power method works here. Okay, and then so it's able to produce high quality conditional samples. First GAN to work on full ImageNet, and then it has it is a little bit it is faster than WGAN GP because it does not need that backward pass to calculate the gradients. And only the weights need to be normalized. Oh. And so you can see this is the so SN-GAN is in the same same computation time as the regular GANs. And so this this also has more things about where you can push your labels in. So you can do it right at the beginning, at the slightly later stage. You can do it at the end, or you have 4 different ways of doing it. And I think they're saying their method is to add the classification label here, and they have just the adversarial loss instead of a different classification. So it's the conditional what they call it, the conditional stuff we looked at before. So if you have the class labels, then it trains a little bit better, right? Okay, so this is SN-GAN. Do we have any questions? Okay, so we can move forward to self-attention GANs. Okay, so here, okay, so this is just using the transformer, and that's what the equations are. So instead of convolutions, I guess they're using transformers to have the attention. So you have X. Sorry, you have X here, and then you have f of X and g of X. So you take X and you have f of X and g of X here, right? These two, the same transformer stuff. And then you have to go, I think, skip over the third one. So f of X and g of X produces Sij. So f of X and g of X produces Sij, which is this attention map. And, oh, sorry. And Sij is scaled to Bji. And then I think the instructor missed this one. H of xi is another w of xi. So we have h of x. So x also goes in here. So we have f of x. They combine together to form this one. Then we have h of x, and they again combine to form O of j. The b of ij is the rescaled Sij, which comes from f of xi, and then you have O of j, and then O of j, and then xi are connected back up. So this is just the transformer. I guess this one is not shown, the short circuit here, but sorry, this is the O is the tension maps, and so in a higher level, this would be the tension maps, and then we would add yi to the next layer on top of the xi, right? So this is just the transformer, and the salient bits, I guess, is they use spectral normalization to both the generator and the discriminator weights. Use self-attention in both generator and discriminator. And they say they use a slightly different version called the hinge loss. And they have conditional models. So we can use the labels. So these were the first to produce ImageNet samples, the first ImageNet samples. And these were some of the images it generated. So yeah, and it pushed the inception score much higher. So okay, any discussions for self-attention GANs? Okay, we can just move on to big GAN. So so the big GAN is just the scaling of all of the GANs that we've already seen. More layers, more stacks, wider, bigger batch, more compute to see what's possible. Okay, and so this is thrown in there. So I'm not quite sure what this is. Some regularization of the weights, and instead of taking the transpose, taking to make this orthogonal, if W and W transpose that times W is I, then it's orthogonal, right? So if it's not orthogonal, then we make a cost. But this only penalizes the diagonal matrix of W prime W. So they changed it so that W prime W, this operation 1 minus I. So 1 minus I means that this matrix is 1 everywhere except the diagonal. Diagonal is all zeros. And this is the cosine similarity. So assuming this vector here and this vector here do the cosine similarity and just acts exactly like a matrix, but acts, but instead of multiplying the vectors, they do a cosine similarity. So they do this, and I think it helps in adding it to the loss function. They add this regularization to the loss function. Okay, and so there are two GANs, big GAN and big GAN deep. And I think this slide just shows that before they used to have the class have to be concatenated over and over again, but they figured out how to concatenate the data, and then you can send that data over here instead of having to put the class into the data. I think this is from the Z, the actual latent variables. So they figured out how to put the class, so the class doesn't have to be injected every time. Okay, so this is the architecture of big GAN. And as you can see, it's the class is being put in multiple places. So each of these res blocks has the batch norm, ReLU, upsample, convolution, batch norm, ReLU, convolution, and then the short circuit here, I believe. And then some concatenation at the batch norm. And this one, res block, I think this is the last one. But it's a combination of the same things. And this is the big GAN deep. So there's just more of these. And so big GAN can handle 512 by 512 images. And this is the architecture of this is the generator architecture, and then this is the discriminator architecture. So for big GAN, they try to increase the batch size as much as possible. They try to sync the normalization between different stacks, increase model size, make it wider, fuse class information at all levels. So this regularization trick and then the truncation trick. And then they use the hinge loss. And let me skip over these. And that's, oh, sorry, the truncation trick. Truncation trick just means that instead of sampling Z from normal 0, 1, they truncated it to us to a limited range between 0 and 1. Otherwise, like weird stuff happens, I guess. So they can truncate the Z from where they sample it. And I think that parameter is calculated from the training or samples. Okay, and then so this is a more big GAN. I think this is a mixture of two classes where they mixed a dog and a ball here, and the others are just all generated. And then also you can do what they call it, from one image to the other, move from one image to the other, just using the latent variables. And so the intermediate ones have do look good. I mean, you can transform the dog to a bird, and then it does have some semantic, looks like correct things. Okay, so the last architecture is StyleGAN. I mean, for this hour, for the lecture that was given. Okay, so this is the traditional generator. You take Z and then you send it through all of these things, and then it produces an image. Here, the Z is passed through all these layers, and it produces W. And the W is fed through all these different layers and just inputted as a style. The actual thing that starts off is a constant 4 by 4 by 512. So it's always the same. And then there's some noise added at each step. So the Z itself is not going through it. It produces W, and then W is added as style elements. And yeah, and this is just so you take the norm out of xi. Sorry, take the mean out of it, and take the standard deviation, add a different mean and a different mean and a standard deviation to it. So this is the style that you want, and you take the mean out of it, and apparently this works really, really well. Here's a picture of it. I think it's the same boy with, and then you have okay, here are all the source A, and then there's source B. I think trying to do a style transfer of source B into source A. So this one is verified. So this is the original one, and then you see just a little bit of it. I think it took the background, it took something else. I don't know what else. And then here took the background and the hair color changed. Here the I don't know what else changed. Hair color maybe. But it's just taking a little bit, so it all looks the same. And then you can take more of the style, and then you can take coarse style. I'm not sure quite what the styles mean. I don't know if these are the finer styles and these are the coarser styles, but I should read the paper. But this works pretty well. So I think it's supposed to be the same boy, but then the different features being changed. And this one, you have to, the effect of adding noise. If you don't add noise, then it looks very oil painty, but then the other side looks much better if you add noise. So that's the reason they add noise. But yeah, that's the content of the first 2 hours. I think I do have the paper for style again somewhere. Don't know how they do it, but anyway, I think we'll probably discuss more in the next set of lectures on this. But that was the end of the first video. Any questions or discussions?
Thanks. I've reached out to Arshad as we discussed and asked him whether he could continue the theory and finish that up. I'll post an update on Slack if I hear from him over the next couple of days. If not, if there are volunteers to lead that would be great too. So just keep an eye out on Slack and I'll update.
Okay.
Because the idea we discussed last time was continuing the theory, finishing it up, and then going to the homework and collab notebooks, for which there isn't a volunteer either. So if anybody is interested in guiding us through it, more than welcome.
Yep. Okay, great. Yeah, there's still 2 more hours of these stuff here. So
Yeah. And I've reached out. I think Arshad had originally signed up, but we'll see.
Okay.
Whether he's still interested.
Okay. Is there anything we'd like to discuss about GANs? I don't know if this is the latest state-of-the-art stuff, but I'm just following the lectures along. But we're getting pretty good. I don't know if it gets better, or there's some new papers out that are like really, really good. But yeah, okay. If not, then I think we can end. We're almost at time.
Okay, great. Thanks a lot, and see you all next week.
Okay, see you all next week.
Thank you.
Thank you.
All right. Thank
Okay.
you, Martin.